Okay, so this is the Chapter 7 test review for Algebra 2, and the first couple questions ask us to make some graphs of a couple different exponential functions. This first one is y equals e to the 3x, and then minus 5. Now, there's no grid on here, so we're going to have to put in our coordinate axis. So I'm just going to kind of draw my horizontal x-axis there, and my vertical y-axis there. You guys can decide where you want to put it based on where you're going to put your asymptotes, things like that. Let me fix that real quick. Okay, so that'll stop doing that. So when it comes to the equation, all this can be done in the calculator, but I want to point out that this last number here, this negative 5, is something that I can come right now down negative 5, 1, 2, 3, 4, 5, and I can draw my horizontal asymptote. And my graph is either going to live above that or below that the entire time. And so now when I go to my calculator, I need just a couple of points. And really I could do that by hand, but I'm probably still going to use my calculator because of the e. I'm going to do y equals e to the 3x out of the exponent minus 5. If I graph it, I can see it right here, it's following the 5, and then it spikes really fast because of that 3x in the exponent. So I'm going to go to the table, and I'm just looking for a couple of points that seem user-friendly. Now I know that when I see these negative 5s, which is the boundary line, that's not a good number to use because it's too close and it's rounded incorrect. It's rounded to that value. So right here I've got 0, negative 4, which would be right there on the y-axis, and then I'm looking at these other points. I mean, I probably could have graphed this down a little bit to give myself some more room. I mean, this is 15. I don't think I have room to go up 15. Hopefully on the test, Mr. Welch will be better and not give you a problem that's too high up. But as this is, what we're going to end up doing is negative 1, negative 4.95, which would be right down there, close to the value of our. Okay, sorry about that. Got a little interruption. And obviously I could find another point, but like I said, it's going to be way up there. And so at this point we're just going to follow the horizontal boundary and spike. And this one, it really went up fast. Okay, the more points I put in, the more accurate my graph will be, but that should be good enough. Now when it comes to stating the domain and range down here, this graph can go left and right forever. I could use any x value I want. There's no problem with that. So the domain is all real numbers. The range, however, this graph doesn't go up and down forever. It goes up forever, but it can't ever appear below our asymptote. So we would say that y is always above or greater than negative 5. And that's what that graph's doing. Okay, let's look at our second graph here. Same sort of idea. Okay, I'm going to go ahead and draw in my axes. Y-axis, x-axis. I'm going to shift this one down a little bit because I see the plus 4. So just to be safe, I'm going to come down here. And that way maybe it'll be a little bit easier. 1, 2, 3, 4. There's my horizontal asymptote. Now it won't be very good if it comes down, but I know this graph is going to go, it's above the line, so this should work out pretty well. I'm going to go to y equals, clear this out, type it just the way it looks. 1 divided by 3 in parentheses, whoops, 3, close parentheses, raised to the x minus 4 out of the exponent plus 4. And if I graph that, okay, I see that graph coming down, and I go to the table, and I don't want these really big values. 2's at 13. I might be able to put that in. 3's at 7. It'd be 1, 2, 3. There's 4, 5, 6, 7. Be right in there. And 4 is at 5, which would be right there. And then 5 is at 4.3. That's 4 1/3. Over here we said 2 is at 13. That's 7. 8, 9, 10, 11, 12, 13. So sure enough, I have just enough room. Now when it comes to graphing these, I'm going to try to do my best, but it doesn't have to be perfect. I'm just trying to make sure I have the general shape of my curve, little dot to dot, and it's going to follow that asymptote. Try not to bump into it. Try to make sure it's clear that you're staying above it. And the way that we prove that we're staying above it, or make it clear, is through the domain and range. Domain, again, is all real numbers. Here are the y values. The graph is always above positive 4. Now, if that graph, just kind of come over here on the side, if that graph had an asymptote and we did a graph like this graph always stays below that asymptote. So this would be for a range that would be y is less than some number. Okay. Anytime the graph is below the asymptote, it's a less than. All right. So now we want to answer a couple questions about those two graphs. Number 3 says, is number 1 growth or decay? Well, if you look at the way this equation, as you go to the right, it is separating from the asymptote. It's going away from it. That tells me that number 1 is a growth function. And number 2, if you look, it's approximating or closing in on this asymptote. It's going to stay with it forever now. That means that it was a decay graph. You should be able to tell that just by looking at the shape of the graph. All right, number 5, we need to write 2 to the x equals 18 as a logarithm. So I'm going to write log, parentheses and equals. The base of the exponent is the base of the log. That would be 2 right here. And I know every logarithm equals an exponent. If I look at this original problem, the only exponent is this x right here. So this logarithm has to be equal to x. Well, the only thing I haven't used is 18. Now, right now I want to point out, I didn't ask you to solve for x. I just asked you to write it as a logarithm, which we've done, so we're done. We don't need to solve this. Later, we'll do some solving. Right now, it's just about rewrites. Okay, now number 6 says to write the logarithm as an exponential. That's doing the exact opposite. So if you can imagine where this 2 here, the base 2, goes to here, the thing that the logarithm equals becomes its exponent. If we can just make those switches, this should work out really well. So the base of our problem here is 4. So that's the base of our logarithm. And we know that the log always equals the exponent. And since this log is equal to 3, 3 must be the exponent. Leaving me with 2x as what it's equal to. Could I solve this? Yes, but I wasn't asked to do that. I was simply asked to write it as an exponential. Now 7 and 8 ask us to expand and condense some logarithms. When you expand a logarithm, it's important to know how many things are in them. There's an x, a y, a 5, and a z. So that means I'm going to have to write log with parentheses 4 times. The first one would be x squared, then y to the 4th, then 5, and z to the 3rd. Now the rule is that if it came from the numerator, it's positive. Well, that means this one here, the x squared, is positive, and so is the y to the 4th. But anything from the denominator, like the 5 and the z cubed, are subtraction because they came from the denominator. And so now when I go one more step, the rule is that the exponent can come out and sit in front of its logarithm. So this becomes 2 log of x. Notice I'm going to make my l's not look like 1s, plus 4 log of y minus log of 5 minus 3 log of z. That's a fully expanded logarithm. Now with question number 8, I also want to condense the logarithm, which means to do the exact opposite. So first thing I'm going to do is I'm actually going to write a logarithm. Notice it doesn't have a base, so it's base 10. Doesn't really hurt us. I want to know if this is going to have a fraction or not. So I look for any negative signs. If a negative sign exists, that means there will be a fraction. And now I want to be able to build things. Well, I also need to look at the last thing I did, which is these exponents that sit out in front. They need to go back before I really put things into the logarithm. Remember that addition, okay, it meant that these two things are multiplied. So I'm going to take 2, or they're from the numerator and multiplied. 2 times x to the 5th. I get x to the 5th because this 5 becomes an exponent to log. Now because this is a negative log, it must belong in the denominator. So my z goes to the bottom, and that 2 is its exponent. Okay. Let's flip it over and do the last few questions. Number 9 says to evaluate the logarithm. There's actually two different ways to do this, one with the calculator and one by hand. What exponent do you put on 3 to get 81? The answer is 4. Okay, now if I'm not comfortable with that question and it feels a little too hard, or maybe you think it's not a whole number, we're going to have to go into the math button, and I'm going to scroll up to find my log base. I'm going to put the subscript 3 here and the 81 in there, and sure enough it gives me 4. But if I didn't do that, let's say I didn't like that, the other way to do it, is to take the log, just standard base 10 log, of the number that sits a little higher. See, the 81 sits a little bit higher than the 3, which is our base. And we're going to divide it by the log of the base of 3. This is essentially what the calculator is doing when we use that log base button. It still gives us 4. Either way, that should be a pretty easy problem. 10 and 11 are really going to test us to see if we know how to work with logarithms and exponentials. When I look at this, I think a lot about the questions earlier where we did question number 6 and question number 5 and 6, where we wrote it as a logarithm or wrote it as an exponential. Because this has a variable in the exponent, I'm going to have to write it as a logarithm in order to solve. But this plus 3 shouldn't be here. I've really got to remove that and get rid of it. So I'm going to minus 3 from both of them. Gives me 7 to the 2x minus 3 equals 343. Now this should be able to be written as a logarithm. The logarithm's base is the base of the exponent, so this should be base 7. Now remember, every logarithm always equals the exponent, and since my exponent is 2x minus 3, this logarithm must equal the exponent, 2x minus 3. The thing I haven't used yet is 343. Whatever happens here, if there are no variables here, this is just a number that goes in the calculator. So let's take our math log base and do base 7 of 343, and we get 3. So now we have 3 equals 2x minus 3. We can add 3. 2x equals 6. Therefore, x equals 3. And we're done with that. That wasn't so bad. Number 11, very similar idea, except that I have to get the logarithm to become an exponential. Now, ln, remember, has a base of e. Now, this ln is alone. There's not a 4 in front of it. There's not a plus 7 somewhere. So this is actually ready to be changed. Its base is e, so I'm going to do e. And every logarithm equals the exponent. So the exponent in this problem must be 6 equals x minus 2. Well, e to the 6th is just a number I can get from my calculator. 403.43 equals x minus 2. I'm going to add 2, and x will equal 405.43. Now you do have to check, whenever you're working with logarithms, you do have to check your answer. If I put that in here for x, would this inside of the parentheses become negative? Well, the answer is no. It would be 403. So I'm not really worried about it. It should be just fine. The last question is about building an exponential model using exponential regression. So this is all about the calculator. So I'm going to go ahead and go to my stat, and I'm going to edit the data. Let's clear this list. Not sure how big it is. So we're going to clear that list. All right, so we're going to go 1, 2, 3, 4, 5, 6, and 7 for my x values, and for my y values, 7.8, is that just plain 24, 74.5, 231, 716, 2218, and 6878. Alright, so we have our data in there. We're going to slide over to calc, and we want to run an exponential regression. That's the model we were asked to find. There it is, it's option 0. I just arrow down, and here's my answer. Now it's important we know how to write this answer. Okay, it says y equals a. Well, my a is 2.51. 2.51. And then if you look at the calculator, it says times b to the x. Well, I really want to make sure I get the order right. So I'm going to use parentheses for my b. 3.098. I could go 3.1. It's kind of up to you. You make those decisions. I don't want to round too much. And that's raised to the x. And that should be it. As a side note, since I've got you here, what I'm going to do is I'm actually going to graph this. I want to show you what we just did. 2.51 parentheses 3.098 raised to the x. I'm going to turn on my stat plot so I can see the graph of my data. Okay, and so I'm going to have to change my window too, so bear with me here for a minute. My lowest x is 1, so I'll go 0 to 10 sounds about right. My y min will go 0 to 8,000, counting by, let's say, 800. And if we graph it now, you can see the dots, and you can see a graph. It's not a perfect fit. I mean, right there it looks like there's a little issue, but it is a pretty darn good fit for my data. In fact, if I, let me change the window one more time. Let's go ahead and let this go down to negative 1,000, or negative 800, might be better. Alright, let's graph that again so you can kind of see. Yeah, it's just following right through there. It's just a really nice job, a really good graph. So hopefully that's enough to help you out, and we'll see you in class.